Yes, sir.
Hi. So the second question which you asked, what is the question is that how loss of carbon dioxide during formation of atmosphere. One of the reasons is it got buried in deep seas, but my question is how gas get buried there. Okay, so there is in simple terms, we know that ocean covers around 70%, three-fourth of land mass is just covered by ocean water, and whatever gases we have in the atmosphere or whatever pollution, whatever pollutants or whatever is there in the atmosphere, carbon dioxide mainly, finally it gets, the oceans are like a large heat sink. So it absorbs all the heat and all the gases and carbon dioxide, all those things. Eventually goes into the ocean absorbs it. And then there are certain chemical processes which I don't know whether it's there in the course, but I will. It's called some. I'm not remembering right now, but eventually they end up in the rock bed of the ocean. Like they end up in the rocks. So I think, if I'm not wrong, I don't know exact number, but most of the carbon is buried inside the rock in the ocean. And how it ended up ocean is that ocean being, since it covers the largest part of our Earth's surface, so, and it has a very high heat capacity also, so it absorbs lot of heat. So one other problem related to global warming is that we are aware of the fact that due to the excessive emission of carbon dioxide in the atmosphere, global warming is happening. The temperature of air is rising. But there is another important factor is that which we don't know is that we know that, but the normal people we don't know that the oceans are also warming up very rapidly because all the pollution, all the carbon dioxide which we are ending up into the atmosphere, at the end it eventually goes into the ocean. So, and they are weathering, or so you can search on the Google. There's something called acidification, ocean acidification. So there is a limit to which the ocean can absorb the this all the carbon dioxide. So once that limit is reached, it would be very difficult. The system, what is called tipping point. You can also search something called tipping point. What are climate tipping points? You can search what is climate tipping points. So those are important topics related to climate change and all. So that's why oceans are very important because everything gets eventually ends up in the ocean. So what last class I was not able to take last class last Sunday because I had some health issues. So that's why there will be one class today, and tomorrow also regular timing. I will be taking class from 4 to 6 Sunday also. Just share the screen. So I'll just start because maybe what's the time? It's maybe I'll wait 2 3 minutes more. Then I will start at 4:10 p.m. So most of the class today also I'll be solving questions, and then towards the end, since we have started thermodynamics, atmospheric thermodynamics, so I will cover 3 4 topics related to thermodynamics, and then from the next class we will start from tomorrow we'll start a very important topic called the stability of the atmosphere. So just start. Okay, so today first I will solve some of the questions related to assignment 4, which you must have done. So all these questions are very important because if you are going to take, suppose if you are going to take this course in your future studies, so we all studied I studied these topics when I got into my PhD first year because I didn't have MSc atmospheric science, those kind of things. So these are very important questions. So if you are able to solve it here right now, it will be very helpful in case you want to study this atmospheric science future. So okay, so the first question of assignment 4, week 4 was, so what is the pressure exerted by water vapor at 273 Kelvin having density of 4.77 gram per centimeter cube. So you have been given some water vapor which is at some temperature 0 degree centigrade, 273 Kelvin, and the density of water vapor is 4.77 gram per centimeter cube. So simple question, they have asked what is the pressure exerted by water vapor. Now you know that in atmosphere we have, suppose we take any volume of air, so it will have different gases, plus it will have also water vapors. It will have dry air consisting of CO2, nitrogen, oxygen, and also it will have some water vapor, that is liquid part in the vaporized form, water in the vaporized form. Now we know that the total pressure exerted by all the gas which is situated inside this volume V can be written as the sum of the partial pressure exerted by the individual gases. So total pressure is equal to the pressure exerted by some dry air, also the pressure exerted by water vapor. So pressure exerted by water vapor is denoted by the small e term. So this is the total pressure. So, and these are the partial pressures. So the total pressure exerted by the entire air within this volume V is the sum of the pressure exerted by the individual components. So in this volume there is some water vapor. They have not given us any dry air. So they have only asked what is the pressure exerted by the water vapor, that is E. So from the gas law, from the ideal gas law, we know that pressure is equal to rho R T. Okay. So pressure exerted by water vapor means E is equal to density of water vapor, the specific gas constant of water vapor, times the temperature at which the water vapor is. So simply you will just write it as density is given is 4.77 gram. You will convert it into kg per meter cube. So 10 to the power minus 3 kilogram per meter cube times the specific gas constant for water vapor. So this is nothing but the universal gas constant R star upon the molecular mass of water vapor times the temperature 273 Kelvin. So when you solve this, you will get something like 8.314 water vapor 18 grams per mole. So grams you will convert into kg. So kilograms per mole. There's some unit which will cancel out. So finally you will get, when you solve this, you finally what you'll get is 601.47 Pascal. So we know that 1 millibar or 1 hectopascal is equal to 100 Pascal. So in the unit of hectopascal, just divide by 100, it will come out to be 6.01 hectopascal. So this is the pressure which is exerted by water vapor. Now just compare it with the pressure which is exerted, which atmospheric pressure. Atmospheric pressure is roughly the order of 1013 point something 12 hectopascal. So almost 2 order of degree difference is there. So the pressure exerted by water vapor is very, very small compared to the pressure which is exerted by the air. And the role of density becomes very important because the density is very different of water vapor with the dry air. So third is the correct option. Now second question was if the atmosphere contains, I think there is some problem with this question because let us solve. First, I will just first solve the question and then we'll see the answer is matching or not. So the question is if the atmosphere contains oxygen and nitrogen to 79% and 21% of the atmosphere. So these are the relative contribution of nitrogen and oxygen to the entire mass. What is the mean molecular mass of the, just wait. What is the mean molecular mass of the atmosphere, which contains 79% oxygen and 21% nitrogen? So this is just opposite. So let us solve this question. Question 2. So they have given that in our atmosphere, nitrogen is present 21%. Oxygen occupies 79% of the total atmospheric mass, which is not what we see in our atmosphere. It is just opposite. But I think there is some typo in the question. So, but let us solve question using this information only. Then we know that first of all, there is a formula for calculating the mean molecular mass. Mean molecular mass given by m bar, which is equal to summation I m of I divided by summation I small mi by capital Mi, where small mi is relative fraction of gases included, gases which are present. Okay, like there is a relative fraction for nitrogen here is 0.21, for oxygen it is 0.79. Okay, and capital Mi is you all know is the molar mass of gas. So we just solved it. So we'll just use this information. So M of I, where I is your gases. For example, there are two gases, so I is 1 or 2. One is for nitrogen, second is oxygen. So it will be 0.21 plus 0.79. So basically your numerator is always 1 because if you add all the contribution, it will always be equal to 1 because the entire mass of the atmosphere is fractional mass is like if you just add all those terms, it will equal to 1 divided by 0.21 upon the molar mass of the nitrogen gas, which is 28 plus 0.79 divided by oxygen is 32. So it comes out to be roughly equal to 31.06 gram per mole. Okay, so this is very obvious also because see, first of all, let's see the answer. The answer is given 28.75, which is not correct because of the fact you see that oxygen is consisting of 79% and nitrogen is consisting of 21%. And nitrogen mass is around 28 molar mass, oxygen molar mass is around 32. Since the maximum contribution is coming from oxygen, so your mean molecular mass will also be close to the oxygen mass. It cannot be 28.75 as given in the answer. So there is some misprinting in the answer. Other way round, if we just take nitrogen to be 79% and oxygen to be 21%, in that case, it will just calculate the mean molecular mass. That will come out to be 1 upon 0.79 divided by 28, 0.21 divided by 32. This will come out to be equal to 28.75, which makes sense because nitrogen is the major constituent of the atmosphere, and hence the total mean molecular mass will be close to the nitrogen mean molar mass, which is around 28. So you can just cross-verify your answer in such a way, because I have seen that in this NPTEL assignment, they upload some wrong answers also. So don't get bothered by the wrong answer. So yeah, there are two ways. So for the 28.75 gram per moles answer, you need to have nitrogen to be 79% and oxygen to be 21%. So in that case, you will get this answer 28.75. Okay. Now the third question is a virtual temperature. Now in the last class we did some derivation of the virtual temperature. So virtual temperature, the expression for virtual temperature is T upon 1 minus E upon P, 1 minus epsilon, where E is the vapor pressure, P is the total atmospheric pressure, epsilon is the ratio of the ratio of the specific heat constant for the dry air upon the water vapor, RD upon RV, which is around 0.622. Now, the virtual temperature is a fictitious temperature, which we did the derivation last class. It comes into picture when we are trying to accommodate the role of moisture or water vapor. Okay, if you are trying to incorporate the role of moisture or water vapor into the ideal gas law, so we did some derivation. So your ideal gas, if you want to represent moisture into the ideal gas law, then you do some derivation at the end. You just replace your so this is the ideal gas law for moist air, which is P is equal to rho times RD times TV. So this TV is the virtual temperature, and its expression is given by T upon 1 minus E by P, 1 minus epsilon. So naturally in the question they have asked you that virtual temperature depends mainly on what? So it's moisture concentration, because the concept of virtual temperature comes only when we include moisture into our ideal gas law. So direct question, third A is the right answer. Fourth question was, what is the geopotential at a particular point in the atmosphere? Now, to answer this, we can just go to the definition of geopotential. So geopotential we defined in that class is the potential of the Earth's gravity field, or it is the amount of work done to raise an object of mass m by height h in vertical direction. So obviously the geopotential is a function of height. So if you want to raise an object by some height h, you need to do some work against the gravity, and that is quantified using geopotential. Okay, so the answer is simply height. So geopotential mainly depends upon height. So the higher you want to raise a mass, higher geopotential will be there. So for this answer is what? It mainly depends upon the height. Okay. Now fifth question was, what is the thickness of dry air between 1000 and 500 millibar surface? So for that we covered, I think we solved some question also using hypsometric equation. So the thickness of the atmospheric layer is given by, suppose you have two layer. This is P1, this is P2, this is a height Z1 and this is a height Z2, and this is your Earth surface Z is equal to 0. So so the thickness, that is Z2 minus Z1, often referred to as ZT, is given by this formula, which derivation we already did, RdT bar R dt bar by G log of P1 upon P2, where T bar is the mean temperature of this layer. So mean temperature they have already given, the question is 5 degrees centigrade or 278 Kelvin. RD you know is 287, so you just solve it. 287 times 278 divided by 9.8. Gravity doesn't change much in vertical direction, and in our atmosphere. And P1 is what? P1 is 1000 hectopascal, and P2 is 500 millibar. So you just solve this, log of 2 it will come. So it will come out to be around 5643 meter. So this is the thickness of the dry air which is situated between these two pressure levels, P1 and P2. So simply using hypsometric equation, you can find the thickness of the dry air lying between two pressure surface. Important thing is to know the mean temperature of the air lying between these two surfaces. Okay, now the sixth question was, the atmosphere of Venus consists of 95% CO2 and 5% nitrogen. What is the mean molecular mass? Similarly, just like we solved the last question, you'll just use same formula. 95% is carbon dioxide plus 5% is, what is it? 5% is nitrogen, N2, by volume. Similarly, you will just divide by 44, which is the mean molar mass of carbon dioxide, C plus O2, 32 plus 12, 0.05 by 28. So it will come out to be 1 upon 0.0215. Let me solve this, plus 0.00178. It will come out to be 42.78 gram per mole. So this is the mean molecular mass of the Venusian atmosphere, given that Venus contains 95% carbon dioxide and 5% nitrogen. Okay. So this is, if you just compare with the, I think for Earth, it's what? I think it's around 28 point something, right? So you can see that the Venus, the atmosphere is denser because it's almost not on 1.6 or 1.5 times the mean molecular mass of the air on the Venus is heavier than what it is on the Earth. So it is around 1.5 times. Okay. Simply because carbon dioxide is heavier, because carbon dioxide molar mass is 44. It contains 95% of Venus atmosphere, whereas on Earth, nitrogen is the most dominant, and nitrogen molar mass is 28. So that's why where all the difference is coming from. Okay, so now the next question was, a parcel of moist air has a total pressure of, so a parcel is there, it is moist air, it has a total pressure of 975 hectopascal and a temperature of 15 degrees centigrade. If the mixing ratio is 1.80 gram per kg and vapor pressure, now again this is wrong, vapor pressure cannot be this high. So there was some misprinting, so I think the correct value of vapor pressure here is, I don't know what, just wait, just tell you. I think it's around 2.82 millibar. Okay. So what is the virtual temperature of the parcel? So virtual temperature of the parcel, the formula is TV is T times 1 plus E upon P 1 minus epsilon. So T is given as 15 degrees centigrade, which is 288 Kelvin, times 1 plus E is 2.82 millibar. Total pressure is 975 millibar. 1 minus 0.622, where epsilon is RV upon RD. Oh, sorry, RD upon RV, I think. RD upon RB. So you just divide 287 by 461.5. You get 0.622. Okay. So when you solve this, what you get is 1 minus 0.622 times 2.82 divided by 975 plus 1 into 288. So 288.3. 288.3 Kelvin is the virtual temperature. So this is wrong again. This is wrong. Okay. So there's, I think last day I was trying, so there is some problem in the question. The vapor pressure cannot be this high. And if you will just put in this vapor pressure of 724, then also you will not get 126 degree. You will get something around 380 Kelvin or something like that, which is also not correct. Okay. Now the eighth question is, in gas equation, Pc is equal to RT. The parameter C is known as, we know that in ideal gas law, P is equal to rho RT. If you take rho on this side, it will become P alpha or Pc is equal to RT, where C is nothing but 1 by rho. Rho is density, so C is called, C has a unit of meter cube per kg. It is a specific volume occupied per unit mass. Okay, so it is specific volume of gas. So C is 1 by rho, which has unit of density inverse. So it is the volume occupied by per unit mass. Okay, so it is called the specific volume of gas. Now, in a thermodynamic system, a closed system is a type of thermodynamic system where there is no exchange within the boundaries of the system. A closed system is the one which doesn't exchange any mass. A closed system is the one which doesn't exchange any mass with the surroundings. Okay, and an open system is the one which exchange mass as well as energy from the boundaries of the system. So these are like simple thermodynamic questions. Now the 10th question was, if at 0 degree centigrade, the density of dry air alone is 1.275 kilogram per meter cube, and the density of water vapor is 4.77 into 10 to the power minus 3 kilogram per meter cube, what is the total pressure exerted by a mixture of dry air and water vapor? So this is the first thing which I was telling you today. 10. So you have a mixture. We have a mixture of dry air and water vapor. So they have asked you what is the total pressure exerted by the mixture of dry air and water vapor. So total pressure exerted is equal to the pressure exerted by the dry air plus the partial pressure exerted by the water vapor. Now this is using ideal gas law. It will be rho times rho d RD T plus rho V RV T. Okay, where rho d and rho v are the density of water vapor, dry air and water vapor respectively. RD and RV are the specific gas constant of dry air and water vapor respectively. So density is given is 1.275. RD we all know is 287 joules per kilogram per Kelvin. Temperature is 273 Kelvin given in the question. Plus rho v is given 4.77 into 10 to the power minus 3 kilogram per meter cube. RV is, we know is 461.5 joule per kilogram per Kelvin into 273. Now when you solve this question, you'll solve this, it will take 273 common because it will come out to be 365.92 plus 2.20. It will come out 100,498.495 Pascal or in hectopascal it will be 1004.98. So this is the total pressure which is exerted by the mixture of dry air and water vapor. So obviously you can just imagine that the major contribution is coming from the dry air, because the water vapor exerts very small amount of pressure. Vapor pressure is very small. This is called the vapor pressure. So E is very small, and the maximum dominant contribution is coming from the dry air. The difference mainly coming because of the large difference in the density of dry air and the water vapor. On one hand, the density of dry air is 1.275 kilogram per meter cube. Water vapor is into 4.7 into 10 to the power minus 3 kilograms. So 1000 magnitude difference is there if you just take the ratio. Okay, so 1004 point. So I think B is the correct answer. Now the density of moist air is, what is the relation between the density of moist air and the density of dry air? So I think you must be knowing this. You must have solved this because I did it in first class, I think. What will be the answer? Like you all know, but why? Which is lighter? Any answer? You can type on the chat box. Which is lighter, moist air or dry air? No, if you want to know the density, you have the ideal gas law. So you can from ideal gas you can compute which would be denser. You know that P is equal to rho RT. So density of so we just take I did it in first class. Yeah, moisture is less dense because you just take the ratio. Density is inversely proportional to R. At a given pressure and temperature, density is inversely proportional to the specific constant. So density of rho upon rho v is equal to RV upon RD. So density of RV is equal to RD upon RV. Now RD is what? 287. RV is what? 461. So just take the ratio between these two. 0.62. So the density of water vapor is 0.62 times the density of dry air. So your moist air is lighter than the dense air, dry air. Okay. So, and the ratio of the gas constant, okay, this is RD by RV. We already know RD by RV is what? RD by RV is 0.62. So, 12th. So I think, yeah, so these were the questions. I think not very difficult if you know basic ideal gas law and some of the properties like the total pressure exerted by the mixture of gases is equal to the sum of the partial pressure exerted by individual components. Then you will be able to solve the question. Now I will again ask you a couple of more questions which I have framed. It's not in your, I think, in your assignment. The question is, there is one more term which will come. If mixing ratio, this is a new term. What is mixing ratio? If mixing ratio of air parcel is 2 gram per kg and the pressure is, surrounding pressure is 1020 millibar, then what will be the vapor pressure? What will be the vapor pressure? So there is a new term which we have introduced in this question is mixing ratio. What is mixing ratio? So mixing ratio often given by this term R, denoted by this term R, is the amount of water vapor there in, it is a ratio of the water vapor, mass of water vapor to the mass of dry air, or in other word, density of vapor with density of dry air. So in simple terms, if the question it is given 2 gram per kg, that means you have 2 gram of water vapor in 1 kilogram of dry air. So this tells you what is the amount of water vapor per unit kilogram of dry air. So the mixing ratio here is 2 gram per kg. So if you convert gram into kg, it will be 2 into 10 to the power minus 3. Since it is a ratio, it is unitless. So it will be 0.002. So this air parcel which we have has 2 gram of water vapor in 1 kilogram of dry air. So this is mixing ratio. Now the question they have asked is, what is the vapor pressure? So how to find the vapor pressure? Now, since from the mixing ratio definition, you know that mixing ratios is can be defined as rho v upon rho d. So since you know density, and as soon as you see density, you remember there is a ideal gas law, which can, from ideal gas law, you can just substitute rho with P and RT. Okay, so we know that for dry air, PD is rho d RD times T, and for water vapor, the vapor pressure is given as rho v RVT. These two equations you know from the ideal gas law. So just substitute it here. So you'll use these two here. So what you'll get is rho v. Rho v can be written as E upon RVT, and rho d can be written as PD upon RDT. Temperature is constant because the environment temperature is constant. So TT cancel out. What we are left with is E times RD by RV is nothing but epsilon PD. So you know the mixing ratio, you know epsilon, you have to calculate E. How to calculate E? Now we know that total pressure is equal to partial pressure exerted by dry air plus partial pressure exerted by water vapor pressure. So from 3 you can write PD as T minus E. Use it here, substitute it here. So it will become R is equal to E epsilon, PD is P minus E. Now you just put the value. The total pressure is given as 1020. This is total pressure. So total pressure is 1020 MB. So R is 0.002. E is what you have to calculate. Epsilon is 0.622, ratio of the two specific specific gas constant. Total pressure is 1020 minus E. So just multiply it, you'll just solve it. 1020 times 0.002 minus 0.002 times E is equal to 0.622. So it will become 2.04 is equal to 0.624 E. So from E will be what? It will come out to be 3.269 or in 3.27 hectopascal. So see, just by knowing the mixing ratio and the ambient pressure and temperature, you are able to find the vapor pressure. So this way, given mixing ratio of air parcel, you can find what is the pressure which will be exerted by the vapor pressure. So you just need to know what is the definition of mixing ratio. It is the ratio of the density of vapor with the density of dry air. And then you can just substitute using ideal gas law. You can substitute and find out the answer. Then you can also find what is the virtual temperature. So for virtual temperature, you just okay, you know this, you know all these things, you know, and calculate the virtual temperature. Okay, is this clear? Is this question clear to both of you?
Yes, sir.
Okay. Now another question shall solve. The question is, now another term is specific humidity. I'm solving some questions and introducing new terms because these terms will be there. You will hear it a lot in the future classes. The specific humidity of a sample of air is 0.0196 at some temperature 303 Kelvin. Find its virtual temperature, that is the sample's virtual temperature. This is first part. Second part, if total pressure P of moist air is 1014 hectopascal, what is its density? What is its density? Density means you have to find what is rho v. No, not rho v, but the density of the moist air. So it will have both, since the sample of air, you have to find the density of the sample of air. First thing to note is that the sample of air this sample of air contains water vapor. Why? Because specific humidity. Now, humidity means you have some water vapor. The terms humid means what? You must be aware. It's very humid. We generally say in our normal language that in summers that it is very humid. That is we get lot of sweating and all. So, if there is humidity, that means that air is not dry. It contains some amount of water vapor. So, specific humidity is nothing, but it is also the same thing. Specific humidity is also same as the mixing ratio. It is given by mv upon md, or density of vapor upon the density of dry air. So this is specific humidity. It is a quantity which tells you the amount of water vapor situated in a 1 kilogram of dry air. So what is the ratio of the water vapor situated in your sample? So that is specific humidity. Okay. Now this is given the question. It is 0.0196. That means what? The last question we had mixing ratio. So we can also say that it is also kind of specific humidity, which is 0.002. So that means you have 19.6 gram of water vapor per 1 kilogram of dry air. Okay, so that is what it means. Specific humidity tells you. Okay, so specific humidity is given in the question is 0.0196, and temperature is given to be 303 Kelvin, which is roughly 30 degrees centigrade. Find its virtual temperature. Now, virtual temperature we know is this formula T plus 1 upon E upon P 1 minus epsilon. Okay, so how to solve it? So for we know P is given as 1014. So P is also given in the question in this next part. So we know T is 303, P is 1014 hectopascal, epsilon is 0.622. We don't know E, so we need to calculate E. So using this mixing ratio specific humidity, we can calculate E. How? Because we know Q is equal to rho V by rho D. And again, using this ideal gas law, we can write it as what we can write. We can write it as E upon RVT, and this we can write as PD upon RDT. TT cancel. It will become epsilon E upon PD. And PD is what? Total pressure minus vapor pressure. Okay. So we know Q is 0.0196 is equal to 0.622 times E upon total pressure is 1014 NSE. So when you will solve this, you will get something as 19.87 is equal to 0.6416 E. So from here your vapor pressure comes out to be 30.96 hectopascal. Okay. So vapor pressure is 30.96. Now in the last question, the vapor pressure we calculated was 3.27. Why? So you can just compare that last, it is now the vapor pressure is almost 10 times what it was earlier. Earlier it was 3.27. Now the vapor pressure is almost 31 hectopascals. So there are, why? Because of the fact that there is larger amount of water vapor per kilogram of dry air. It is around 20 gram of water vapor you have in 1 kilogram of dry air. Whereas earlier you had only 2 gram of water vapor. So since the water vapor is also almost 10 times in this current new sample, that's why your vapor pressure is also just almost 10 times what it was earlier. So vapor pressure is also a function of amount of water vapor which is situated in a dry air. So it is makes sense. So this is the vapor pressure. Now you know E, so you can easily calculate, put this value E in back into here, and you can calculate virtual temperature. I have done this calculation. It comes out to be 306.5 Kelvin. So this is your virtual temperature. Now the next part of the question was, if the total pressure of moist air is 1014, what is density? Okay. Now we know that P is equal to rho times RD times TV. Now this is the ideal gas law for moist air. So here your density rho is entire density, rho d plus rho v. Okay. So we just we formed this when we were doing the derivation in the last class. So we know that P is 1014 hectopascal or 10 to the power 2 Pascal divided by RD is 287 joules per kilogram per Kelvin. TV we have calculated 306.5 Kelvin is equal to rho. So when you just calculate the moisture, the density of the moist air will come out to be 1.15 kilogram per meter cube. Or you could have separately also calculated, like you know what is P is equal to PD is equal to rho D RDT, and E is equal to rho V RVT. You calculate separately. You know what is PD, you know what is E, you know what is temperature, and RD, RV you know. So you can calculate rho D and rho V and add them. But it is a long process. So simple process that since you've already calculated what's your temperature, just divide the total pressure by the RD times TV. You will get the density of the moist air. So these are few kind of questions which can come in your exam related to the like mixing ratio, specific humidity, find the virtual temperature or the vapor pressure. Okay. So 2-3 formulas are there. So using those formulas, you can easily solve the questions. So now what I will do is that I will start with the teaching part. Like I will teach 3-4 new topics today, and then a couple of questions also will solve in the later part. Okay, so now what you're going to do is that we'll try to study. So we're studying thermodynamics of moist air, so we'll try to know what is specific heat. Specific heat. Okay. So you must have heard this term a lot of times in your thermodynamics course. But now we are trying to understand specific heat with respect to atmosphere. Like when you're trying to study atmospheric thermodynamics, and what are the terms, typical values of the specific heat which we use in our calculations in atmospheric thermodynamics. So to start with, we'll start with what is the definition of specific heat. So suppose if you add dq amount of heat, dq amount of heat to unit mass of substance. Unit mass means one unit mass, suppose 1 kilogram. Unit mass of any substance such that the substance temperature changes from some initial temperature T naught, changes from initial temperature T say to some final temperature T plus dT. So there is a dT increase in temperature without any phase change. Without any phase change. So you are supplying some amount of heat to any system. Maybe you are applying some heat to some liquid. So there is no phase change. So liquid is not changing into vapor. So it is remaining liquid. This is one of the condition. In this scenario, the quantity dq by dt is called the specific heat. So this quantity dq by dt is called, this quantity is called specific heat. So if you simple terms, if you are supplying any system with some amount of energy, dq energy, then a part of the energy will be utilized in increasing the temperature of the system or increasing the internal energy of the system from say T to T plus dt. So in that case, the ratio dq by dt is called the specific heat. Okay. So because simple first law of thermodynamics also comes into picture. So you have first law of thermodynamics. So it states that if you add some amount of heat to any system, a part of the energy will be utilized in changing the internal energy of the system given by du, and another part of the energy will be utilized by the gas in doing some work, dw, against the environment. So this is the first law of thermodynamics based on the conservation of energy. So if you supply dq amount of heat to any system, a part of this energy will be utilized in changing its internal energy by du amount, and a part of the energy will be used in doing some work by the gas. Suppose you are supplying this energy to some gas, that gas will do some work against the environment, dw. Okay, so this is your first law of thermodynamics. Okay. Now, suppose we are talking about specific heat, and we know specific heat is given by dq by dt. Now, in atmospheric dynamics, there are basically two important concepts of specific heat. First is specific heat at constant volume. Specific heat at constant volume given by Cv. This is the term Cv. Okay. And the second, which we'll study little later, is the specific heat at constant pressure, which is given by Cp. Now, what is Cv? Suppose we know the first law, dq is equal to du plus dw, where dq is the amount of heat which is provided and du is the internal energy, dw is the work done. Now, as the word suggests, specific heat at constant volume, suppose you are adding some dq amount of energy to any system consisting of gas such that there is no work done. So whatever heat you are supplying is utilized in raising the internal energy, because you know that dw is what? You must know is pdv. So since it is a constant volume, so this term goes out. So whatever dq you are supplying to the system is entirely utilized in changing the energy of system by amount du. And you know that internal energy of the system U is directly proportional to temperature. So that means whatever energy you are providing to the system is used to change the temperature of the system by some amount dt. Okay. So we know that dq by dt at constant volume is called Cv, specific heat at constant volume. And since here your PdV is 0, so from equation 1, dq is what? Du. So we can also write Cv as du by dt. Okay. So you can write the change in internal energy du as nothing but Cv times dt. This is important term. So the change in internal energy is nothing but the product of the specific heat at constant volume Cv times the change in temperature. Okay, so there is no work done, so PdV goes to 0. So whatever energy you are providing is entirely used in changing the temperature of the system by dt amount. So this is called a specific heat at constant volume. Now comes the second term, which is specific heat at constant pressure. Just like in the last case, we are supplying some energy to the system such that no work was done. System was not expanding, so PdV was 0. Now suppose you are adding some amount of heat to a system, dq amount of heat, such that a part of heat will be used to raise the internal energy to the system, and the part of it will be used to do some work. Now there is no more any constraint of constant volume, so dV is not equal to 0 in this case. There is some work done. Okay. And in that case, the specific heat at constant pressure, so the change in whatever heat you are supplying, part of it will be utilized in increasing temperature of system by dt amount, and another part of it will be used to do some work. Okay, so dq by dt at constant pressure is given by Cp. Now what is the value of Cp? So in simple terms, you can write as dq as Cp dt. Okay, now this value of Cv and Cp are different to each other. Now you may ask why. Now another important question arises. Are Cp and Cv different? And if yes, then which is larger, Cp or Cv? Now, you can solve this question without doing any maths. You can just sit and think, and you can solve this question by just knowing what is happening. Now, in the first case, you are trying to provide a system some energy dq such that the system is held at constant volume. The system is held at constant volume means there is no work done, PdV 0. So the entire heat is used in increasing its temperature by dT amounts. Okay. So there is some amount of heat dq. That is Cv. Now in second case, you are applying, you want to change the temperature of that system by same amount dT. But you know that now the work done is not zero. That is a part of heat will be used in doing some work. So in order to raise the temperature by same amount dT, since some amount of energy goes in doing some work, you need to provide larger dq, because dq is now getting divided into two parts. A part of it will raise the temperature by dt, and another part of it will do some work. In the earlier case, dq was only used to change the temperature. So genuinely, by common sense, you can understand that in second case, you need to provide more amount of heat. Okay, and in this way, you can say that Cp is greater than Cp, because in second case, you need to provide more amount of heat, and C is nothing but dq by dt. So since in the second case you need to provide more amount of heat, so Cp will be always be greater than Cp, since dq by dt, or because in second case, I will write just like dq for second case is greater than dq for first case. Why? Because you want to raise the temperature by same amount in both the cases, by dt amount. So that's why Cp is greater than Cv, and mathematically also we can prove that. Proof question. Mathematically derived relation between these two terms. Relation between Cp and Cv, and show that Cp is larger than Cv. So we'll start with the first law. Anything you just start with the first law, which is dq is equal to du plus dw. Okay. Now we know that du can be written as Cv dt, and dw is work done, pdv. This we all know. Du is Cv dt. We have derived here. Du is Cv dt. This is first. Now you want to derive establish the relation between Cv and Cv. Now from ideal gas law, know that P alpha is equal to RT. So you differentiate them. Differentiate above. You will get P d alpha plus alpha dp is equal to R dt. R is a constant, so its differentiation will be 0. So R dt. Now just use 2 in 1. If you'll use 2 in 1, you'll get dq is equal to cv dt pd. Okay, sorry. You can write v as alpha, because since we're talking about the per unit mass, so volume per unit mass is nothing but alpha. So you can just write it as cv dt plus, now pd alpha can be written as r dt minus alpha dp. Okay, so your dq is take cv plus r times dt minus alpha dp. Okay, now this term in bracket is what it's called as cp, because at constant pressure this term will go and your cp will be what? dq by dt. Okay, so now from equation, this name is 3. From 3 you can say that cp is equal to cv plus r, or cp minus cv is r. So this is a relation between cp and cv, and this r is a positive quantity. Now since r is positive quantity, that means cp is always greater than. This implies that cp is always greater than. So the specific gas, specific constant, a specific heat at constant pressure is always greater than specific heat constant volume. Now, all these things we are talking about is at molecular level, but what about the atmosphere? Okay, so in order to understand that, we'll understand what is known as the law of equipartition of energy. All these relations, I think you must have done many times in your thermodynamics course in BSc Physics. Now comes, because we want to derive the the value of Cp and Cv for atmosphere. Okay, not some gas level, but for atmosphere. So law of equipartition of energy. So what does it tell is that so it just tells us that if a system is in thermal equilibrium, if a system is in thermal equilibrium, then with each degree of freedom, some equal amount of energy is associated, or each degree of freedom will contribute equal amount of energy. In mathematics, you can say that, for example, you have one atom or molecule. That energy is equal to half times kBT. Where kB is a Boltzmann constant, T is a temperature. So this amount of energy is, for each degree of freedom, this amount of energy will be contributed. Suppose you have n number of atoms. So you will have half times Na kBT. Now this kinetic energy is what? Is nothing but, can be written as in thermodynamics CVT. So CVT is half times Na kBT. So your CV is half times Na times Kb, or this is also can be written as half times R star, because R star is Na times Kb. So the value of specific heat Cv at constant volume is equal to half times R star. But this is for each degree of freedom. Okay. Now suppose you have some similarly for Mayer's relation Cp minus Cv is equal to R, or R star, you can say that Cp will be three by two R dash, right? Yes. But remember, these two are for each 1 degree of freedom. Now suppose you have a monoatomic gas. Monoatomic gas, like suppose for monoatomic gas like argon and everything. So your degree of freedom is what? So you need to calculate for degree of freedom. So degree of freedom, there's formula for this 2n plus 1, where n is the number of atoms. So for monoatomic gas, n is equal to 1. So the degree of freedom associated with the monoatomic gas is 3. Okay. So in that case, your Cv will be, for monoatomic gas, 3 by 2 R dash, 3 by 2 R star, because there are 3 degree of freedom. Each degree of freedom contributes half. Okay. So I think I should not write this. This is confusing last. Because we've already calculated it for each degree of freedom is this. So for 3 degree of freedom, it will be 3 by 2 R star. So for so similarly, we can calculate Cp for monoatomic gas. It will come out to be 5 by 2 R star. Okay. Now for diatomic gas, you have like our atmosphere mainly has nitrogen and oxygen, which are diatomic gas. So for atmosphere purpose, we will use this case. So degree of freedom is what? Since we have 2 diatomic gas to 2n plus 1, it will be 5. So we have diatomic gas of 5 degree of freedom associated with them. So in that case, each degree of freedom will contribute half kBt. So Cv for diatomic gas is 5 by 2 R star, and hence you see P for diatomic gas is 7 by 2 R star. So the ratio of Cv, the question which comes in exam is ratio Cv by Cp for monoatomic is 3:5, right? And similarly, ratio for Cv by Cp for diatomic gases 5:7. Now atmosphere mainly has these type of gases. Our atmosphere mainly have nitrogen, oxygen, which are diatomic gases. So now what we will do is that we will define the value of the specific heats for atmosphere for dry air. So for that, what we'll do is that simply we will just for our atmosphere. For atmosphere, we are talking about the collection of gases. So it will have both different diatomic gases, nitrogen, oxygen, and everything. So for that, what we'll do is that we'll define the specific constant at constant volume, CVD. Now we'll just omit diatomic because we know the atmosphere only is diatomic gas. So we'll use CVD is equal to CV is 5 by 2R. 5 by 2 R star divided by mass of a dry air. Okay. Now this is nothing but 5 by 2 times RD. We just calculate it. So it will come out to be 2.5 times 287 joules per kilogram per Kelvin. So it is an important number. So the specific constant at so a specific heat at constant volume for a dry air for atmosphere is 717. If you just multiply these two terms, it will come out to 717.5 joules per kilogram per Kelvin. This is an important number. Similarly, CPD, the specific heat at constant pressure, is 7 by 2 R star upon MD. So it will come out to be 3.5 times 287 joules per kilogram per Kelvin, which is equal to 1000. Very important term, you need to remember this, 1004.5 CPD. This is CPD. This is specific heat constant pressure. So these two are very important terms. So we can just derived it from basics. Okay. So, and obviously when we do the difference between these two, CP minus CPD minus CPV, that is 1004.5 minus 717. What you will get is RD, which is 287 specific gas constant for dry air, 287 joules per kilogram. So why we are studying is that because when we'll study in the atmosphere, there are a lot of processes goes on in which there is an exchange of heat also, some case little amount of. So in order to understand those heat exchange, we need to understand these two terms. Specific if the heat exchange is taking place at constant pressure, we will use these terms, and if the heat exchange is taking place constant volume, we will use this. Mainly for atmospheric process, this term is very important, CP. CPD 1000, we generally take it as 1005 joules per kilogram per Kelvin. So, okay. Similarly, you can also calculate it. For example, you may be, calculate this. We have calculated for dry air. Now calculate for vapor. Calculates specific heat at constant volume for a vapor and for specific heat at constant pressure, CPV and CVV. How to do that? Simple. You'll use same formula, 5 by 2 R star. The only difference is that CVV will be 5 by 2 R star upon mass of water vapor, not MD. So it will be 5 by 2 times RV, and which is 461.5. So this will come out to be 1615.25. Similarly, at constant pressure, the specific heat at constant pressure for water vapor is equal to 7 by 2 R star upon MV. So this will come out to be 3.5 times 461.5, which is equal to 1153.75. Okay. Now again, the difference between CP and CV will come out to be 461.5. So these are some important terms, but which will be utilized later for solving questions. So these are what is specific heat is all about. The most important term is this one. (1005). Okay. So now I will start with another important term, which is called enthalpy. Okay, enthalpy in layman language, in common terms, it is the measure of the total heat content of a system. Total heat content of a system. System can consist of gas. Okay, so this is the next thing which we'll understand. I'll just not solve question related to enthalpy, but we'll just understand what is enthalpy, and then we'll introduce a very important term. It's called dry static energy. Just give me 1 minute. Just come. Okay, so what is enthalpy? So definition wise, if heat is added to the system, if heat is added to the system or a material at constant pressure, suppose you are adding heat to some system at constant pressure, so that specific volume, so that the system's specific volume changes from some initial value alpha 1 to alpha 2. So there is basically some expansion, maybe you can say, that you're providing some heat to the system, and that heat is you're providing a constant pressure. So a part of heat is utilized in expanding a system from some initial volume alpha 1 to alpha 2. Then obviously if there is some expansion, then there's change in volume, and whenever there is change in volume, there is some amount of work which is done. So the work done by the unit mass of that system, by a unit mass of system, work done is what? P times change in volume will be, you're taking this is taking place, heat is adding place at constant pressure, so P is not changing. So there is some amount of, so say the amount of work done, delta W at constant pressure P is P alpha 2 minus alpha 1. So alpha 2 is the final specific volume and alpha 1 is the initial volume. Okay. So this is amount of work done. So total change in heat. So change in heat or dq. What will be dq in this case? We already did this while deriving Cp, that when you're adding heat to a system, what will happen is that using first law, if you're adding heat to a system, a part of it will be utilized is changing its internal energy, U2 minus U1. And another part will be used in doing some expansion, P alpha 2 minus alpha 1. So this is your dq, this is your du term, and this is dw term, first law of thermodynamics. You do some rearrangement, collect all the u2 terms. So u2 plus P alpha 2 minus u1 plus P alpha 1. So just rearranging first this into this. Now this change in heat can be written as the difference in the quantity given in brackets H2 minus H1. So if you're providing some heat to a system at constant pressure, then a part of energy will be used in changing the internal energy, another part will be used to change this volume. So if you do some rearrangement using first law of thermodynamics, you will get these quantities in bracket, and these quantities in bracket are called enthalpy, where H is U plus P alpha. This is called enthalpy of the system. This is the initial enthalpy. This is some final enthalpy. Okay, so it is a sum of internal energy plus pressure times specific volume. Or in simple terms, it is a measure of energy, total energy. Measure of energy, not total, but measure of energy of system. Okay, now this is your equation. Your enthalpy is U plus P alpha. Okay, now what you do is that you just differentiate this term A. Why we are doing is that we want to derive the value for H. So we'll just differentiate A. So we'll get d of H is equal to d of U plus P d alpha plus alpha dP. This is equation B. Okay. Now we know from first law that dq is equal to du plus P d alpha. This we know. So using C in B, we get dH is equal to dq plus alpha dP, or you get the second form of your first law of thermodynamics, which is dq is equal to dH minus alpha dP. Now, this is very important. This is called second form of first law of thermodynamics. What is the first form? First form is dq is equal to du plus Pd alpha. This is your first form. This is your first form of first law of thermodynamics. So by just doing some rearrangement, we get this. Both are equivalent. Okay. So this is called the second form of first law of thermodynamics. So dq is equal to dH minus alpha dP. So what is your H? So here you can write this as dq is equal to Cp dt minus alpha dP. Okay, so here your H is, you compare these two equations. So your H is nothing but Cpt. Okay, so your H can be substituted as Cpt. So H is equal to U plus P alpha, and then also H can be written as Cpt. So now we'll try to, we know that dq is equal to dH minus alpha dP. Now we'll try to derive the dry static energy. Now we know that dq is equal to second form dH minus alpha dp. And we also know from the hydrostatic equation that dp by dz is equal to minus rho g, or it can be written as minus g upon alpha because rho is 1 by alpha. Okay. And from definition of geopotential also we know. So we are collecting all the concepts which we have. So from geopotential definition we know that d phi is equal to g dz. Now this can be written as g dz can be written as from here g dz. If you take g dz, maybe you just g dz can be written as minus dp by rho, which is alpha dp. Okay, so you just replace this alpha dp minus alpha dp with g dz in this equation. So you get your first law, dq is equal to dh plus g dz, and g dz is nothing but geopotential. So dh plus df phi. So dq is nothing but dh plus phi, or your h is what? Enthalpy cpt. So this quantity which you are seeing in the bracket cpt plus phi is conserved in nature. So now I will tell you, after doing all the derivation, now I will tell you the significance of this term. So suppose if you have air parcel, if you have some air parcel whose mass is fixed, with fixed mass, it is not exchanging any mass from its surrounding, and that air parcel is moving, which is moving in an hydrostatic atmosphere. Why hydrostatic? Because our atmosphere is, we do some hydrostatic approximation. By hydrostatic approximation, we mean that in our day-to-day life, the atmosphere which we have, in the vertical direction, the pressure gradient force is balanced by the gravitational of the earth, dp by dz minus rho g. So if we have some air parcel which is moving in an hydrostatic approximation, which is this we have done in this derivation, in that case, the quantity given by h plus phi, which is called the dry static energy, is conserved. Only or provided the parcel, the air parcel, neither gains nor loses any heat to the surrounding. In other words, your dq is zero, adiabatic process. There comes another topic, adiabatic process, that is dq is zero. Okay. So you have an air parcel. It is moving in some hydrostatic equilibrium atmosphere. Atmosphere which is in hydrostatic equilibrium. Okay, and the air parcel is adiabatic in nature. The process is adiabatic. Air parcel doesn't exchange any heat. doesn't exchange heat with surroundings. Doesn't exchange heat with surrounding. In that case, your dq, which is equal to dH plus phi, which is equal to H is nothing but CPT plus phi, is 0. Process is adiabatic, dq is 0. So d of CPT plus phi is 0. In that case, CPT plus phi is some constant. Okay. And it is conserved. So this is called the dry static energy. So to take away message is that for an adiabatic processes, your dry static energy CPT plus phi, why it's called dry? It is conserved. For adiabatic processes in atmosphere, the dry static energy is always conserved. Why it is called dry? Another question. It is called dry because we have not taken into consideration the role of water vapor here. It's just dry air. So what in atmospheric thermodynamics, if we add moisture into it, then it will become moist static energy. Then you will have some another term which will get added, which is called LV times Q, which Q is your specific humidity, LV is the latent heat of vaporization or condensation. This is moist static energy. But here we are not dealing with moist static energy till now. So since we don't have moisture LVQ term, we only have CPT plus phi. It is called dry static energy. So it is always conserved for adiabatic processes in our atmosphere. Okay. So to remember is that CPT plus phi is conserved for adiabatic processes. Now the last topic for today's class will be not question. I'm talking about air parcel every time. But what is like some of the properties of the air parcel? Okay, so what is an air parcel? So it is a small control volume it is a small control volume such that it satisfies following properties. So this is very important, very necessary. If they ask in interview also, what are some of the property that air parcel should satisfy. So why do we need air parcel? Suppose we are trying to understand any processes in the atmosphere, for example, the motion of air from one place to another. So we cannot just pick the entire atmosphere and talk about it. We have to choose certain control volume, some small dV volume, and then we apply all the equation of motion and all those things for that volume. We study that motion of the air parcel, and then we generalize it for the entire. So first we take a small control volume. So that control volume is known as air parcel, and some of the properties that an air parcel need to satisfy is that it exists in the environment. It exists in the environment which is in hydrostatic equilibrium, which is a very good approximation for our practical purposes. Because we know in practical purposes, in vertical direction, the pressure gradient force is balanced by the Earth's gravitational fields. dP by dz is equal to minus rho g. So that air partial should exist in an environment which is in hydrostatic equilibrium. On Earth, this approximation is very valid. Second is the air parcel does not mix with surroundings. So the air partial, the control volume dV which you have, should not be mixing with the surrounding. It is withholding its identity. It is not getting lost. It is intact. So the parcel is not mixing with the surrounding. The third approximation is the parcel the parcel's movement does not disturb the environment. The parcel's movement does not disturb the environment. The fourth is parcel's rising and sinking motion. The parcel is rising or it is sinking. Should be adiabatic in nature, which we just should be adiabatic. Adiabatic means the parcel should not exchange any heat from its surrounding. Now this is a very valid approximation because in our atmosphere, since the thermal conductivity of air is very less, the air is kind of insulator, so thermal conductivity is very less. So this approximation is very valid because since the thermal conductivity of air is less, it does not there's not a lot of heat which gets exchanged between the surrounding with the parcel. So parcel does not exchange much of the heat with the surrounding. So adiabatic property is also very well valid in our atmosphere. And the last and very important is that at any given level, the parcel and environment environment means the surrounding. The parcel and the surrounding should be at same pressure. What does it mean is that suppose you have some air, this is your earth, you take some parcel from close to earth's surface, some dV volume of air, and this air is going in the up direction. Now we know that pressure drops as we go up, pressure decays exponentially as we go up. Okay, so in the same way, if the parcel is also this parcel is moving upward, so the pressure which is there inside the parcel should be exactly equal to the pressure at that level. So parcel is adjusting its pressure with the pressure of the surrounding. There is no difference in the pressure between the surrounding and the parcel. So that is one important concept. So these are some of the important properties of the air parcel. So this now we'll do with the last topic, that is dry adiabatic lapse rate. So this is a very important concept. It just tells you, as the name suggests, lapse rate. Lapse rate means the change in temperature with height. Dry means you're talking about the change in temperature with dry air. There is no moisture in it. Adiabatic means the process is adiabatic in nature. As the air parcel is moving in the upward direction, it is not exchanging any heat with its surrounding. Okay, it is expanding in nature, so it is not exchanging any heat